Have you ever wondered why continents look like pieces of a giant jigsaw puzzle? Or why earthquakes and volcanoes occur where they do? Today, we'll uncover the fascinating story of how Earth's outer shell moves and reshapes itself, a theory that revolutionized geology, plate tectonics. This theory explains mountains, earthquakes, volcanoes, and even the shape of our continents. By the end of this video, you'll understand how the Earth works beneath your feet. So stay tuned and don't forget to hit subscribe for more geology insights. Section 1. The birth of a theory. In the late 19th century, scientists struggled to explain Earth's surface features. Two major ideas emerged. First, the Earth contraction theory, the idea that Earth cooled and shrank like a drying apple, creating wrinkles that formed mountains. This explained compressional features like fold-thrust mountain belts, but failed to explain rift valleys and ocean basins. Nor could it explain the shapes and positions of the continents. Shift tone to intrigue. Second, the Earth expansion theory, suggesting Earth was heating and expanding, breaking continents apart. This explained rifts, but not mountain belts. Then came Alfred Wegener, a German meteorologist in the early 1900s. He noticed the jigsaw fit of continents across the Atlantic and proposed the continental drift theory. Wegener argued that continents once formed a supercontinent called Pangaea, which broke apart about 200 million years ago. His evidence? Fossil distribution, ancient glaciations, and matching rock formations across continents. But Wegener faced a big problem. He couldn't explain how continents moved. He thought they slid over ocean floors, but geophysicists said friction would make that impossible. So his theory was dismissed, until new evidence emerged decades later. Section 2. Magnetic evidence and paleomagnetism. In the 1950s, scientists discovered that Earth's magnetic field leaves a permanent signature in rocks. This was a game changer. Here's how it works. Earth acts like a giant magnet with lines of force running from pole to pole. When molten rock cools below the Curie temperature, about 580 degrees Celsius for magnetite, its magnetic minerals lock in the direction and angle of the magnetic field at that time. This angle, called magnetic inclination, varies with latitude, so by measuring it, we can tell where the rock formed relative to the poles. When scientists studied ancient rocks in Europe and North America, they found something odd. The magnetic poles seemed to wander, but along different paths for each continent. The only logical explanation? The continents themselves had moved. This was the first solid evidence for continental drift. And it didn't stop there. Later, scientists discovered that Earth's magnetic field reverses polarity every few 100,000 years. North becomes south, and vice versa. These reversals became the key to unlocking the next big discovery, seafloor spreading. Imagine a lava flow cooling today. It records the current magnetic field. If another flow cools after a reversal, its magnetism points the opposite way. Stack these flows and you have a timeline of Earth's magnetic history. Section 3. Seafloor spreading. During World War II, ocean floor mapping revealed two striking features: mid-ocean ridges, long mountain chains under the sea, and deep trenches near continental margins. Then came a surprise. Magnetic surveys showed stripes of alternating polarity on the seafloor. Scientists realized these stripes recorded Earth's magnetic reversals. Here's the process. New crust forms at ridges as magma rises and cools, taking on the magnetic signature of the time. When polarity flips, New crust records the opposite direction. This pattern proved that the ocean floor spreads outward from ridges. But if new crust is created, old crust must be destroyed. That happens at trenches, where oceanic plates sink back into the mantle, a process called subduction. The mid-Atlantic ridge is pushing North America and Europe apart at about 2.5 centimeters per year. That's roughly the speed your fingernails grow. Section 4. Plate Tectonics Theory. Combining continental drift and seafloor spreading gave birth to the plate tectonics theory, the unifying theory of geology. Earth's outer shell is divided into rigid plates about 100 kilometers thick, floating on the ductile asthenosphere. These plates move horizontally, carrying continents and ocean floors with them. Most earthquakes occur along plate boundaries, while plate interiors remain relatively stable. This explains why geologic activity is concentrated in certain zones. Example, the Pacific Plate is moving northwest at about 8 centimeters per year, making it one of the fastest plates. That's why the Pacific Rim is so volcanically active. It's literally riding the edge of a tectonic conveyor belt. Section 5. Types of plate boundaries. There are 3 main types of plate boundaries. Number 1, divergent boundaries. Plates move apart at mid-ocean ridges, creating new crust. Sediment is thin near ridges and thickens away from them. Example, the mid-Atlantic ridge is splitting Iceland in 2. Number 2, convergent boundaries. Plates collide. Oceanic plates subduct beneath others, forming trenches and volcanic arcs. Example, the Andes Mountains formed as the Nazca Plate subducted beneath South America. The Mariana Trench, the deepest point on Earth, marks another subduction zone. Number 3, transform boundaries. Plates slide past each other horizontally. Example, the San Andreas Fault in California produces frequent earthquakes as the Pacific Plate grinds past the North American Plate. Section 6. Hotspots and causes of plate tectonics. Not all volcanoes occur at plate boundaries. Hotspots, plumes of hot mantle, create chains of volcanoes like Hawaii. As plates move over a stationary hotspot, volcanoes form and then go extinct, leaving a trail of islands. But what drives plate motion? Scientists believe it's a combination of mantle convection, ridge push, and slab pull. Hot mantle rises at ridges, pushing plates apart, while sink slabs at trenches, pulling plates down. Example, the Hawaiian Islands showed the Pacific Plate's motion over millions of years. The Big Island is still over the hotspot, while older islands like Kauai are eroding away. Together, these forces, convection, ridge push, and slab pull, power the engine of plate tectonics. Think of it like a giant conveyor belt powered by heat from Earth's interior. From Wegener's bold idea to modern GPS measurements, plate tectonics has transformed our understanding of Earth. It explains mountains, earthquakes, volcanoes, and the very shape of continents. Thanks for watching. If you enjoyed this deep dive into Earth science, hit like, subscribe, and share. And let me know in the comments, which part of plate tectonics fascinated you the most?